Okay, we can apply this technique in different scales, from the micro scale or to the mega scale. So see, MIT Media Lab. Okay, and this one here is another example. I think this is a person from Sweden. He's trying to present his design, and he used Kickstarter to promote the product he designed. So actually he designed a kind of basic unit, so that you use this element, you can build this kind of aesthetic structure. Yeah, this is like a helmet structure.
Juggling ball can move from one place to another and back again. When he realized those holes made the blocks lighter and easier to hold on to, he built the rest of them the same way. The only difference now is he makes them with plastic instead of wood. This way, they easily snap together or apart,
So this
which
is
means the number
the
of
product
shapes
he
you can
tried to
add
sell.
is limitless. Lately, you can find Eric traveling around the world performing with ghost cubes. And he's been crowdfunding his system so he can one day produce them on a much larger scale. He wants them to be a tool for creativity and inspiration for everyone.
My guess is that the number of variations that you can create with this method is infinite. If I find one variation that has 2 layers, I can just keep adding layers of 3, 4, 5, and so forth. And there's not really a ceiling to that.
What would you build with these blocks?
This all had something to do with origami. The difference is that they cut out some parts instead of using fold to cover this cutout area. Actually, I think Victor, I think your team proposed something like this, right? Or didn't you? Or some other group? I don't remember. No? Okay. But imagine if we use metal and then we cut out this this part, and then maybe you can use something like you can either pull it or kind of a balloon to inflate it and then to create the shape that we want. And also the shape will be controlled by this aesthetic pattern. Then we can control the overall shape of after this inflation. Right now, she is trying to deform this by hand. But still, the overall shape is still controlled by the pattern that you design. Okay, I just come up with one thing. For the structure we have every grid, different sizes, and also because of the construction deformation, the shape is different from the design model. Okay, so maybe if it is possible that we can design this kind of structure uniformly. So we make only one type. But then with this kind of movement, we can pull it in some way, and I think we can also twist it, and then we can fit it onto the panel. Okay? So maybe this is one way of thinking. Try to use uniform object, and then we can use it and then adapt it on the job site for various shapes. Okay, and this various shape might be because of the curved surface, so it's from the design itself, or it might occur because of the structure system displacement. So for example, this structure showing right now in the video, you can adjust the overall distance between the two parts. Breathing facade. So it is an application supposed to for architectural envelope, building envelopes. see these are students' projects. So it's design kind of basic element, and then you join this element to make a two-dimensional expansion. Actually, these are all based on similar idea, but with different type of unit. Okay, and there are much more actually. No, this one? Yeah, we have seen this one. Okay. And this is the website from this MIT Media Lab. If you want to see what they are doing, and there is this one is the research paper. You can download the entire paper from this website. I want to see if we have a volunteer to read and report on this paper for us. Okay. And also from this paper, you'll be able to find more papers. And as graduate student, I would encourage you to put on your effort on reading this kind of research paper. Okay, it will be very helpful for your research. And also to develop the kind of ability to learn from these academic research papers. Okay, this is the website, and here we have some examples. We can make some practice on these aesthetic structures. So here I have this folder, and there are examples. Okay, here I think I start from this kinetics.gh. Okay, so if you download this file, grasshopper file, and then load it, then you can use it. too large. Okay. Okay, so this file is from kinetics. Okay. And it simulates this pattern, consists of large and small squares. So if we try to simulate this here, this is the reset button. So this is the initial situation, and we can pull it. Okay, because this is based on numerical analysis, so when you pull it very quickly, at some point it will violate the constraint. But when you release it, then it will try to find the balance situation to comply with all the constraints. Okay, and we can simulate the behavior of this kind of material. Okay. Okay, so for this one, we need to have the input to describe the pattern. So these are the pattern, and I want you to start to design this pattern using Rhino. You draw this, and for every square, let me fill out then as surfaces so you can see. Okay, so you have solid. I mean, basically, we can start from this checkboard pattern. So we have solid and cavity, solid, cavity. And then for another layer, okay, you can have different dimensions. Okay, and then you use polyline to draw. I would keep a habit using always counterclockwise, drawing these squares or rectangles. And let me close it. Positioning closed. Okay, and then you can just draw a part of it, or using this one, I think. Oh no. The orientation has to be. Okay, if you don't draw it diagonally, perhaps it is more convenient to use this square to draw it. Okay, and then you draw them, and then you make reference to it. For example, this one, it shows only a part of it. So if I restart this. Okay, I have to set preview off. It's gone. Okay, I found that when we have this grep, this kangaroo 2 with this grep on, sometimes it behaves very strangely. And you have to watch out that. But right now, I think the simulation is okay. Okay, so this is only a part of the entire surface configuration. Okay, and if you copy it and array it in some way so that it becomes a larger size, then it can become like this. Okay, so for first step, I want you to start by drawing your own pattern and then reference to this component and then try to see if it works, and then later I will explain how to create this grasshopper script to do the simulation. So you can design your own, and maybe you make some variations and then to work on your design, maybe if you want. I think this one is relatively simpler, okay? So you take a few minutes to start to draw your own figure. Maybe you can take a look at this, for example, this one. Okay, this is the wiki page regarding aesthetic material, or you can find some other examples. Okay, for example, like this one is also one example. This one we can do it using origami. They call it the water bump configuration to make this kind of pattern. And this one is also, I think it's also inspired from origami tessellation pattern for that. Okay, you can start to try to experience this one. And we can start from scratch to make this one. Okay, one thing I learned from doing this, when I turn on this kangaroo solver with grab on, and then I want to go back to work on Rhino canvas, then it's better that you turn this simulation off. Otherwise they interfere with each other, especially when you click the Alt key.
use scissors dulu.
Okay, I see.
Ada caranya yang sudut. Nah, tapi aku coba-coba kok gak bisa. Coba pengen sedikit, sedikit kan nggak ada aslinya ya? Sama sih, nggak ada polygon ya? Agak gimana ya? ternyata salah aku bukan yang itu bawahnya, itu udah terlalu yang auxiliary structures there should be like this.
Okay, let's. Is this okay for your homework? For this load 100, 200, and 300? You can see for load 300, zone A, zone B, and there's no zone C. 1, 2, 3. Okay, and let's check, because I think you have submit 3D mesh, right? But some of you have not submit the 3D model, so let's check the 3D mesh. So let me go to the query, so that I can selectively filter only the zones that I want. So I choose the filter for parent ID, and then, for example, we start from zone A. So now we retrieve all the level 300 record with parent ID zone A. Okay, this one should be removed. Delete record. Okay, so these are the model and the meshes that you have submitted, and let's check on the preview. First I clear all of them and get table log 300 and log. Okay, so these are the panels submitted by Group A. Is it correct? Victor, is it correct? These are the panels that you submitted. Okay, and I want to overlap with the grid view on level 100. So I go back to Airtable. Okay, I go back to Airtable and then turn on the load 100 and also switch to the query grid and set the filter here. Okay, it is okay because I've set the element ID contains grid. So here now on this table it shows only the entry of the grid record. So it will load in this one. If I go to the preview website and then switch to load 100 and get table, load, okay. So now we can see that the panels that Group A have submitted, they are fit onto this grid structure. Okay, so if this preview window are fully developed, then we should be able to click on one of this panel and then it will activate the database and then find all the information regarding this panel for the user. For example, if I want to know who is responsible for design and installation of this panel, then I should be able to click it and then send out a query. Or if I want to check if this panel has been fabricated. Okay, so the factory, maybe the manager, he is supposed to fill out some tables in this database to show the status of this specific panel in the project. Okay, so this is the idea, how we can integrate the design and the fabrication information together in one environment. Okay, and if I want to retrieve the geometric specification of this panel, then I can also click on this one and then the system will access the database and retrieve the shop drawing, okay, or the G code for CNC machine for me, okay, for this specific panel. Okay, so this is the way we organize all our information, and this is the purpose for asking you to do this homework. Okay. So now we can go back to the Airtable and maybe we go on for the load 300 and change the filter. Okay, so not only for Group A, we also want to include Group B. So we switch to parent ID and for Zone B. Huh? All records are filtered? Why? Oh, I didn't choose OR. So this is N. I have to switch to OR. So now it will show not only panels for Zone A, but also panels for Zone B. Okay, and then I can go to here and okay, I mean, this is not well developed. So right now this previewer is not so convenient to use. Okay, and in this case, actually I can load it again. Otherwise, I may have to clear it and then reload it again. Get table and then load. No? Okay. Okay, so now we see the problem. You get it? You are using different coordinate systems. where are group B? Okay, you see the problem? The coordinate system that you use is different from the original one. Okay, somehow when you create the mesh, okay, and also another thing is that, okay, yeah, so they don't match, okay, otherwise they should fit onto this grid structure. Okay. Also, the way you draw each of panel, maybe we have to think about a way to distinguish one panel from the other. Right now, I mean, because this this visualization is poor, so we cannot see how to dissect each of these panels. Okay. Okay, and maybe we can go on to get group C. So this time we can simply remove all the filters. So now it will show all the panels including zone C. Okay, there are 3. Okay. There's something interesting here. We have this mini model here. I think it's because of when you are exporting this mesh, you start from a model using a different unit. Okay. I think, let me see. If you use centimeters, then perhaps you get this one. Okay. And I think this panel is from group C, right? So the coordinate system of this one is okay, but this one is not okay. Okay, so roughly you know what to do, and I haven't checked about this 3D model, but for group A, you still need to upload the Rhino model for each panel here, okay? And then after we have done this, and you start to design the detail of each of these panels, then we can go on for log 400, okay? And it will be roughly similar to this. And also in this case, because we have panels in different shapes, or maybe it's not that necessarily, or perhaps we can have panels, uniform panel, but then we can use this uniform panel and apply it for different sizes or the boundary situation. Okay? And in that case, maybe for each of this panel, we may refer to its type instead of its specific drawing and design. Okay. 3 o'clock. Okay, now I can go to this another exercise. You can go to this aesthetic structure 1. Okay, so this one is okay for you? So I'm going to close it. Okay, let me start from this curve 2. Okay, we start from a unit like this. This is from the perspective view. Okay, this is for aesthetic structure 1. From perspective view, I've drawn, let me bake this out so you can see how I drew this and then reference to it. So I drew them as separated panels. 1 panel, 2 panel, 3 panel, and 4 panels. Okay, so each one were drawn in 1 polyline. Okay, and this one become the basic unit because I want to make an array of this unit to make a 2-dimensional configuration. So we have a 2-dimensional array. Okay, so first I find the boundary surface. This is the curve 2. Make the boundary surface of it. Okay, and then create simple mesh for them, for each of them. For making a surface into a mesh, there are different ways. This is the more common way, which will create a mesh for each breadth. But it may use more complicated mesh. In this case, because we have only squares or rectangles, so we use this simple mesh. So to make sure that it will always use the simplest mesh for the surfaces. So you see these 4 meshes for all of them has 4 vertices and 1 face. And then we join these 4 to make it 1 mesh with 4 surfaces. But this time it has 16 vertices because it doesn't distinguish vertices with exactly the same coordinates. Okay, if we want to remove this duplication, then we use this component called weld vertices, which is also from this mesh category, utility, and where is it? Mesh weld vertices. So after we have done this, originally it has 16 vertices. After we have melded these vertices, become 10 vertices. So 2, 4, 6, 8, and then the center, we have 10 vertices. Okay, and then make an array of it. Okay, this is a rectangle defining how you are going to array it. So the height of the rectangle, this green rectangle, shows the distance for this array in the y-axis. And then the width of this rectangle shows the width, the horizontal distance of this array. And then I want to make 4 by 4, or if you choose this one, 8, and you have 8 by 8. array. So this one, you get a larger one. Okay. Okay, and if you go on, we have this array, and then we deconstruct this entire array to retrieve all the vertices. Here we have 640 vertices. If they are duplicated points, oh, how come we still have so many duplicated? Oh yeah, of course, yes. And that's right. Because we mail the vertex for one unit, not for the entire configuration. Okay, but after we have, no, they should be separated. Oh yeah, okay. First, I simplify it so each unit are separated in one branch, right? Okay, and when I want to find out all the points, then I need to flatten it, and then we remove all the duplicated points, so the number of points are reduced. Now all the points are in one list. Okay, and here I want to check the sphere collide, okay, which means I don't want the vertices of the entire, all these vertices, don't want them to collide with each other. Maybe this is not the most efficient way. Okay, maybe we can do one thing, which is to divide these points into two sets. One on the top and one at the bottom, and then we check collision only for points where are in the same level. Okay, for example, I check collision only for the upper set or only for the lower set, and this will reduce the computation dramatically, I would say. Okay, so these are some ways to make this entire program running more efficiently. So here I check the sphere collide, which is from kangaroo and goals collide. Here, sphere collide. And then we assume that we want to keep each vertex away from each other by the distance of 1, which is 2 times this 0.5, because these R define the radius of the sphere, okay, and then merge them with other goals objects. The other thing, which is we want to fix the shape of all the basic unit. This is the basic unit, and we don't want the basic unit to be deformed, so we have to fix the relative location of all the vertices of each group has 10 points, right? So here we construct the mesh so we get the vertices for each of these units, but they are separated in different branches. For each branch, we want to set rigid point constraint on it. Okay, so each of these basic unit will be fixed. Okay. Let me stop the simulation. Okay, so this is from the mesh, and all the entire model consists of different mesh. I want to show them in the simulation, so I use this show constraint and then add that to merge. Okay, and what's the other part? Actually, these are not. Why are they still here? They should be removed. Okay, and this part, this is to choose one of the unit, and then I want to use it as an anchor. So the entire tessellation, there will be one unit which is chosen based on the slider here, and that entire panel will be anchored on its initial location. Okay, and here I add this grab, and let me switch this, disable this first, and let's do okay. So this is simulating the entire aesthetic structure. Now I can drag it. I think right now it may go off the plane. It is too large. Maybe I should start from a smaller one. Okay, let me turn it off. Start from a smaller one, maybe 2 by 3. Sometimes it happens like that. I don't know why. Okay, now it's good. Okay, so now we can drag it, and it doesn't check for overlapping, so it won't prevent this unit from penetrating each other. Okay, and what happened? If I turn on this, maybe I have to change back to this 4 by 4 tessellation. And then I can use some actuators to control it. Okay, this, let me reset it, and I can show you where I have to reset this actuator to be 1. Before I reset it. Be 1, okay? And if I show you the actuators, then you see where are them. Oh, you see these green lines? They connect the hinge of this unit to its opposite, to the unit opposite to it. So these are actuators. Okay, there are 2 green lines, 2 here, 2 here, 2 here, 2 here. Alternatively, they connect this unit together, and then when I slide on this slider, it tried to change the length of these actuators. Okay, it can be smaller. Oh no, that is this one. It can be smaller than 1, which means the distance, the length is shortened. But when it is larger than 1, which means the distance is extended. So using these actuators, I can control the configuration of it. So if I reduce the distance, doesn't stop. Why is that? Okay. Because I didn't show it. I showed the initial one, but not showing the result for the simulation. So as if I and extend it or shorten it, then I can control the entire situation. And here, this one is anchored, and I can change the anchored. So when I slide here, now this one is anchored, and I can control the actuator. Or I switch another anchor position. Right now, this one is anchored. Okay, and switch to another one. Which one is anchored? I have to see it. Oh yeah, this one. Now this one is anchored. So when you slide through it, it changes the anchored unit according to how you slide through it. Okay, so this is the one for the simulation using this unit. There's another one, the third one, which is based on diagonal pivot. And for the control of it, I also have to switch to curve 3. Let's reset it. Okay. And then use this actuator to control it. So you see the whole structure is twisted. At this point, it's twisted a little bit on the 3D space. Okay. Maybe not exactly like, but similar to the video. And with this, we can experiment different way of tilting this pivot, this hinge. Okay, let me show you the original shape. This is the original shape. This is the original shape. And the first one, which is this one, this one I don't have this actuator, so I will disable this part. And then use grab to control it. Okay. Okay, if you replace these crosses with squares, then you get this box configuration. Now this one is anchored, so if I pull this one in, okay, you see here it exhibits the aesthetic behavior. You see, now if I pull in, so I shorten the diagonal distance, right? So for normal material or normal structure, the other direction perpendicular to this diagonal should be expanded. But in this case, both diagonal direction become smaller. Okay, so this is a kind of aesthetic behavior of aesthetic material. And the proportion, I mean, how much this distance is shortened, there is a spatial variable or spatial term called Poisson ratio. So if the Poisson ratio is negative, then it is aesthetic material. If the Poisson ratio is positive, then it's normal material. Oh, sorry, it's the reverse. It's reverse. Poisson ratio is positive and it shows this aesthetic behavior. Oh yeah, I think I have checked this overlapping prevention or collision detection for all the vertex. So you see when I try to pull it closer, somehow it tries not to penetrating, not for penetration, but for collision of the vertices. They are not quite the same, okay? But in some cases, it will still prevent the penetration between these panels, okay? Okay, maybe you can also try to design your own aesthetic pattern and see if it will also work for that. Okay, we take a break for 5 minutes and then we'll start your presentation. And this time we start from group C, okay? So please prepare for your presentation in this 5 minutes break.
Who first?
How to do it first. You go first.
Oh, it's up to you. You can also first. Because your presentation is from last week, right?
Yeah.
Yeah, maybe you can understand them. But I'm worried if we go last, is it will be enough time for us?
Oh, yeah. But this time we are the second one.
Yeah? Alright, C-A-N-G.
Yeah.
C-A-N-G.
You wanna do presentation first?
No. Why you get medicine?
Huh? Yeah, at the beginning, because I fell, and then the one is kind of infected.
Oh.
So this morning when I come there, they or 4 o'clock.
Oh.
So it has to be now because tomorrow the clinic is closed.
Wow. You hurt where did you hurt?
My knee,
Oh.
and I fell for no reason. So I just walk and then suddenly what?
Wah, ini kan, kau gimana caranya masukkan folder di situ?
Muter sih.
Flash disk ya?
Iya.
Kalau aku pakai lagi, aku bisa nggak?
Bisa. Langsung kan pakai laptop.
Jangan lah ya. Jangan lah ya.
Enggak, kalau saya kan.
Iya. Oh, udah.
Oh, ini Kak, you know already what to upload at the table?
But
I know.
if we upload the online this
Yeah, have you uploaded?
no.
But do you know what to upload, right?
Yeah.
Yeah, okay.
I haven't uploaded.
Yeah. But later you screenshot it and then you submit it in the
Okay.
Yeah.
你我可以跟你要是礼拜上课而已。
我没有放上去啊。
上
真的啊。
上礼拜我看到
OK，好，我们再找。
那我们说另外然后这个接缝在那个 grasshopper 里面就没办法接续上面，那要怎么办？
Grasshopper 里面没有办法编的，它可以。
为什么？
它是 bread，它不是 surf。你用 bread 就可以 reference 到它。然后OK， 那个部分确实是因为我曾经有试过，试着把那个 bread 再把它变成 surface， 但是没有。你知道 bread 跟 surface 的差别？surface 它是用一个数学方程式去描述的一个曲面，所以它其中一个关键就是它必须是在曲率它是连续的。你如果有这种尖角，它就不是连续的。所以呢，在 Rhino 里面，它会把它分成2个 surface， 然后接起来，这时候叫做 poly surface。那 poly surface 其实在 Rhino 里面，它也就是 break。break 就是 B 就是 boundary，rep REP 是 representation， 它的意思就是用 boundary 去 represent 一个几何的一个物件。那其实原先这个是用在封闭的物件，我们一个封闭的物件，你可能是有很多的 surface 去封闭起来，所以它代表的是一个 volume， 是一个 solid。但是 Rhino 它是 surface model， 所以它其实它没有真正的 solid， 但是它是用 surface 去 enclose 一个 solid。好，那3号它的 break 就是我把很多的 surface 接在一起，就叫做 break。好，其实在真正的 solid model 里面其实不是这个样子，不过 Rhino 它用这个方法来做，能够做到大部分的事情。好，那这个因为当初产生这个曲面的时候，我们是用一个 surface 来描述这整个 Mobius tree。可是 Mobius tree 很特别的是，当它过来的时候，它翻了180度，所以以 surface 的这个 geometry 的 representation， 它没有办法把它连起来。所以当它分割变成这一块的时候，那个陈后来老师他想办法去把它接起来，所以这一片其实是有2 设定连接起来。那实际上这其实是连续的，但是3号接不回来，其实应该是有办法，只是很复杂。你们，我的建议是这样，你自己去 create 你自己的这一块。其实重点就是你不一定要跟它完全一样，重点是你这4个点是可以固定在这个4个点。所以你如果用这4个点，你去 create 你的一个设计，你还是可以做。你不一定要平贴在那上面。好，这是一个可能性。另外可能性当然你也可以说，好，那我也切成这2块，那你就上传。
可是它会长
真的吗？
因为我玩的是我们
这是你们设计就可以。那你们一片设计。
一片是
折下去。
然后就刚好刚刚那个地方
那你不管，你只要把那4个点抓出来就好，绝对不要把它。了解我的意思吗？4个点那抓出来，让你们自己去把那个 panel 做出来。好，那到时候安装的时候，那4个点是对的。不过你实际上做的时候，还要去现场量，然后所有的每个 panel 的尺寸要根据现场量的这个。因为你现在是根据模型去做的嘛，对不对？不错啊，你们弄这个是用 Grasshopper 弄出来的，还是直接在 Rhino 上？Victor 好，那你们要跟他学啊。好。Okay. I think we have already got our 5-minute break, so we can start.
Okay, I will talk about designing with curves experiences. This paper is from School of Architecture in USA, Pratt Institute. First is talk about the outline of presentation. Basically, this define to the characteristic of design approach. Second is design approach and design representation. This divided into 4 parts: developable surface reflection, refraction, gadget, drawing closed and open curve, sculpting and post-rationalizing surfaces. First, I will talk about defining design approaches. There's 4 characteristics of design approach. First, the bottom up or top down. Bottom up, it means the logic of create pattern and drawing drive the design process, and designer evaluate the result. But top down is the opposite. It means the decision making before, hence means that the designer has to make up his mind about what the model is supposed to be like before beginning the design process. Then can in some cases represent a strong design goal, but it can also become less relevant in process. Second is about periodic knowledge of geometry. The reason related to previously occurring knowledge in geometry again play a significant role in design approach. As a designer, decision can make influenced by the knowledge of mathematical model. For example, this knowledge is different to knowledge obtained from observation and experiments, and can help in characterization approach. The third, exploiting material properties. This based on material usage, The material-driven process requires little mathematical knowledge, but relies heavily on technical knowledge, the knowledge that is transferred via the repeated physical manipulation of folding of paper. This can also be described as bottom-up approach based on material logics. Basically, this design approach talk about folding of paper, but we can learn from paper to make metal folding. And the last part is use the digital tool to make 3D model or 2D model, which means that designer looks at static model will work on it. Second, the relative simulation of folding crisp pattern that include rolling. A designer can see how the crisp version of curved crisp fold in real time. So this for design properties divide into four way. First, the development surface reflection is use the model. This refraction the gadget is use the software too, but the drawing open and closed curve and sculpting on post rational seeing surface is used analog is manual. First, the developable surface reflections, geometry and design representation. This for geometry aspect, we can imagine the general cylinder and cut with the plane with subsequences mirror and rotate like the figure. The rolling as the parallels creates the pattern cones can manipulate in similar way. This for references before using this method. As we can see the figure at the figure 3 at the left, a model based on general cylinder at Black Mountain College. We can assume that designer could consider of creating a cylindrical shape of enclosed which can achieve with cylinders reflections. The process can start by defining constant in input surfaces, namely the two edges of bench that touch the ground. Defining of design approach of this method. Basically, subsequent steps consist of reflecting the cut part of placing and the resulting curved trace. The designer continues this process step by step. Approach can also apply to cone and tandem surface. This part we using Rhino, and also can use the Oriflame software.
This is a plugin for Rhino?
I think so.
Yeah, 211, so it has been there for 10 years.
Yeah.
Okay.
And then the surface has input surface, and there's used manipulating a local coordinate system to orient the reflection plate. The cones are cut with planes parallel to based on the axis. The example shows that peeling of parting cones that share an apex A. So this is the second way to design for the geometry and design representation. The position of curve and rolling is creates pattern, and we can create the discrete version of gadget. This is software Freeform Origami by Tomohiro Tachi. Mr. Tachi. The historical reference and precedence. He interpreted ray in optic as rolling and exploited the diffraction properties of the tectonics to redirect the rollings. As we can see the diagram here, using the refracting lines with the three ways, hyperbola, parabola, and eclipse. For the First, hyperbola. The body of a hyperbola can be used to refract ray on either side of the curve. On the left side of left side here, the ring can be made of one of the both sides of the curve on the right side, like here. Parallel ray on the concave side of parabola refract toward its focus on the left, like this, and the inverse configuration pushes fully away from the focus on the right, like this. The last one is the ellipse. The ray converging towards on one focus of ellipse gets refracted like this on the left side, and the role of the focus are inverted on the right side like this. And there are rare hand drawing sketches relevant that you can drawing in images with designing a new model, like in figure 12, use corresponding gadget for inner ellipse. And this for this approach can be seen as constraint propaganda system, in which paper is the computer. In the first example, a single ellipse is divided into two parts. One is as mountain, another as a valley, like figure number 14, like below. Just the two examples with same parabola gadget. And cylindrical configuration could be achieved in bottom example, like here. In the figure 16, in this 16 consists a regular tiling made with a hyperbola gadget. Expand of Guzman interpretation of optics can be asked a designer to use any of gadget and do substantially than using freeform origami. Many cases for which women with wrong mathematical conjures can be used for simulation. The regression representation is approximation that doesn't necessarily follow mathematical constraints. For the third, this manual or analog ways to make shape geometrically and design representation. Design with curve should consist of concentric curve and should have a hole in the center. Design based on freehand curve no consists on curve but may not foldable. No practical disease prevention exists for software, so design approach has to practical analog is manual. The models could be 3D scanned and post-rationalized using algorithms. This is a reference of this method. In addition to provide us real instance of an artist sharing this method. Definition of the design approach. The configuration requires a hole at the center like this. And it's an important character of design approach, allow designer to explore the degree of the model can be folded. And the last way to design the surfaces, sculpting and post-rationalizing curved surface. This iterative analog process similar to wave curves. So basically, just draw the pattern and fold it by hand, just like this. Extend this approach by using curve crease and developing a national system to keep track change. The process starts with clamping or sculpting a sheet of soft paper, just like figure in the below. Designer mark the mountain and valley in subsequently flatten and shear to decrease pattern. So the result and analysis for this way to develop the surfaces, develop surface reflection by top down and bottom up is particularly used top down, and the rest of geometry is quite medium. Material driven is no need. Digitally driven is used. So for the reflection gadget, we can do both top down or bottom up, and must have knowledge of geometry but no need material driven. So and no need digitally driven. For drawing open and close curve, use bottom up design approach. This method is quite low in knowledge of geometry, but this is must have knowledge for material usage in this method. Digitally driven, it can be, but not must. Sculpting and post-rationalizing surface can be top down, and knowledge of geometry is quite low. The material driven is quite important in this method. And finally, the digital driven is can be partially. So the conclusion: the mathematical behavior of curve grace cannot be fully describable yet. Result in lack of available digital tools. Designing with curve grace can occur in several ways, and purpose for design approach to digital to analog that can help designer to make curve grace scaffolding. Reference in history of curve grace that can help in defining alternative design approach and adhering to categories in geometry is useful in some cases. Regarding this digital design approach, designer can easily explore cone, cylinder, and tangent surface. The proposed refraction gadget can be used for simulation, but expensive exploration are difficult. It is unclear which grace pattern have well-defined surface configuration. Analog design approach provide the potential for formal exploration, but rely on basic knowledge rather than a priori geometric knowledge. In this case, it's very difficult to combine the process of making model by hands with digital tools. The evolution of the design approach via characteristic and design representation may help designers who want to use this subset of geometry. Illustrating the limitation and constraint of design approach may individually future work and open problems. Okay, thank you. Any questions?
Have you can you post the link to the paper
Link.
on the Moodle?
Link. Oh yeah. Okay.
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 Okay. And can you turn to the slide where it shows some geometry analysis for curve folding? Maybe go to the earlier slide,
Earlier.
which explain the geometry of this curve folding. Yeah, number 7.
Oh, this one.
Okay, I think this one is very important. You understand this one? Can you explain why is that?
What?
Why is that? We have a surface which is planar, so we can curve it like that. I think which is consisting of cylindrical surfaces,
Yeah.
and then we define a plane, cut this surface, so we derive a curved section, right?
Yeah.
And then we take the bottom part and then find the reflection of this bottom geometry to the plane, and then we derive the figure on the right hand side. Okay?
Yeah.
So with this geometric analysis, we can simulate or we can predict what is the result of folding
Yeah.
this paper along this curved crease. Okay, can you understand why is that?
Oh.
And because this paper is also described bottom up and top down.
Yeah.
So when we do analysis like this, you think this is bottom up or top down?
This is bottom up for me.
Yeah. Yeah. So if you want to make a top down analysis, which means we have to be able to describe the result first.
Yeah.
This is what we want. And then the process will lead us to
Cool.
the deriving of the curve
Yeah.
crease. Okay? And this is bottom up because we have this curve crease first.
Yeah.
And then with this process, we can predict what is the outcome. Okay, and I'm not quite sure, but based on what the author says in this paper,
Mm-hmm.
he say we need both bottom up and the top down approach, or as designers we need more top down than bottom up. What do you think?
Oh, I think yes. For designer must be
Yeah.
top down.
Top down.
Yeah, but must know the all the process from bottom up to make.
So both of them.
Yeah, both
we
of
need to know both
Yeah,
the
yeah.
top down and bottom up. I think at the beginning, he listed like four issues we need to go through.
Yeah.
Earlier slides.
Yeah. For. Yeah.
Number four, the characteristics
Oh yeah.
of a design approach. Okay, so first we need bottom up and top down, right?
Yeah.
And we need priori knowledge of geometry.
Yeah.
Okay, and explore eating material properties. So using different material, the result might be
Yeah.
different, or the process can be different.
Yeah.
And also we need to
Digital.
make use of digital tools. Okay, but I think the number 7 slide is very important. It's very simple, okay? But after you get to know this, then you understand a lot more about curve creasing. Okay, and why is that? Because the refraction of this bottom part shows another alternative static state
Yeah.
of the whole configuration. Okay, all the intermediate states are not stable. I mean, it will be difficult to continuously transform the original shape to its refracted part. The process can be very difficult, or even you may destroy the material. Okay? But the shape before reflection or after reflection, both of them are geometrically static. So imagine if you are able to cut it along this curved crease and then rejoin the shape on the reflection side. That should be not so difficult,
Yeah.
right?
Yeah.
But if we have to transform the material continuously from one state to the other
Yeah.
state. I think the intermediate process is difficult. Okay, it can be very difficult. Okay, but somehow the two extreme, they are two static states of this configuration. Okay, and okay, go on for later slides. There is one slide regarding parabola and the.
Oh, parabola. Yeah.
Okay,
This one.
can you explain this? We have all studied this conic curves, right?
Conic curve, yeah.
We have hyperbola, parabola,
Parabola,
and
okay.
ellipse.
Ellipse.
Okay. How these three types of curve are derived from a cone? We have a cone. We always start from the cone, right? When we are in the high school,
Yeah.
how you get parabola? How you cut this cone to get a parabola section? You cut it parallel
Yeah.
to the side, right? Okay? And if you tilt this cutting plane toward this part, then what do you get? You get ellipse, right? When this is parallel to the side, then you get parabola. Okay? When you tilt it more horizontally, then you have intersection here and here. So you will get a closed curve. So this is ellipse. Okay? When you tilt it more vertically, then you get something like this, but this is not a parabola, this is hyperbola. Okay? And remember when we talk about curved surfaces, remember based on Gaussian curvature, we have three types of curved surfaces. One is positive surfaces, something like this. One is developable, which means the Gaussian curvature is 0. Yes. And one is negative. You get hyperbolic surfaces, which is this. So they are all related. And also, if you look at this rulers, oh, sorry, you don't see. You just take a look at these rulers. You see these lines? They are rulers. So if it is a hyperbola, then all these reflections on one side, I mean this rule and this rule, they are reflection against this tangent direction of this curve. Okay, so on one side, these rules going to intersect at the same point, and also for the other side, they are always also get intersection at the other side. So this is the geometric characteristics of a hyperbola. But when this is a parabola, then you find this reflection on both sides of the tangent direction of this parabola. Then you find on one side is parallel rules, the other side is concentric configuration. Okay, and when it is ellipse, then you find on one side they are diverge. Okay, these lines diverge, become wider and wider, and they never intersect. But if you extend on the other side, they will intersect somewhere here. Okay, and from the other side, they are concentric to the focus of this ellipse. Okay, okay, and then if you fold it to its reflection, then you move from here to here. So on this side, these rulers are divergent, and this side they are also divergent. And for parabola surface, if you fold these curved creases, become like this, then they swap. Okay, parallel on the left hand side, now parallel on the right hand side. Okay, and then concentric on the right hand side, and now they are divergent on the other side. Okay, so I think this figure makes it very clear for us to understand the geometric characteristics of